Hi you guys, and welcome to chapter 18, gas exchange. So in this chapter we're going to be looking at, as this picture shows, what happens after air is coming into an alveolus and then it needs to cross over into the capillary, it needs to attach onto a red blood cell, it needs to be transported. So all that mechanism we'll be talking about, that exchange and that transport. So specifically we'll be looking at, first of all, properties of gases. How do they move from where to where, and just sort of a little bit of the physics of gases. Next, a gas exchange through capillaries. Transport in the blood. How does it move around from place to place, given that it's not very soluble in water or in blood? And also carbon dioxide transport. We want to know how it gets from place to place. We'll also look at a regulation of respiration and the automaticity of it, and what part of the brain is in control of that. So first of all, the movement of a gas is going to be very different if that gas is moving in air or if that gas is moving in a liquid, correct? That makes sense. In water, moving a gas inside of water or moving it in the air is going to be quite different. And the reason we want to talk about that is because you're moving it in the air when you get it into your lungs and into your alveoli, and then you're moving it in a liquid when you're moving it in blood and transporting it to the different cells. And there's my little guy transporting oxygen within a capillary. So what's going to influence the efficiency of this movement? How well you can do that, how well you can move gases around. So as I said earlier, we're moving oxygen through air into the alveoli and then through a fluid into the blood and into the tissues. Very hard thing to do. Transporting it in two different mediums is not an easy task. So the efficiency of that gas exchange is going to depend on a few things. The first one here that I'm bringing up is the structure of the respiratory membrane. So these are alveoli in this picture, and there's arteries and veins coming to them and branching into the small capillaries that you can see here. So blood is coming in deoxygenized and loading up with oxygen at the level of the alveoli. So in order to do that, see if this all makes sense. The bigger the surface area of those alveoli, the better it will be. The more oxygen you'll be able to captivate, correct? So think of all the alveoli, of all these little balls, and if you have them all intact and functioning well, then you're going to have a huge surface area that's going to allow you to utilize all that surface to captivate that oxygen. If, however, you have emphysema and some of these are destroyed, let's destroy some of these like this, and you're destroying some of these surfaces because you've damaged your lung, then that surface area is going to be reduced and getting that oxygen is going to be more difficult. So next we want to look at concentration gradient. And what is the concentration gradient of that gas? And we're going to not call it concentration gradient, we're going to call it partial pressure. So when we're talking about a gas, we no longer talk about it as a concentration gradient, but as a pressure, as a partial pressure. It's the same concept that we looked at before when we looked at solutes. So in this diagram here, you have an alveolus, and it's going to be it's full of oxygen, and this oxygen can pass over to the capillaries, and carbon dioxide here, for example, will go the other way. It'll be picked up. But the only way that can happen is if the partial pressure, let's do the first step. The only way you can deliver some of that oxygen here is if there is a concentration gradient, if there's more oxygen in the alveolus than there is in the capillary. If not, it's not going to go there. So we call that partial pressure. So the partial pressure in the alveolus has to be higher than that of the capillary. If not, it will not move there. Okay, and the other way around for carbon dioxide. Carbon dioxide here has to be in a higher concentration, or better said, at a higher partial pressure. And if it's at a higher partial pressure, then it will be able to travel back into the alveolus, and then you're going to exhale it out. Okay, so surface area 1, concentration gradient 2. What else? We want to look at membrane thickness. So what if this alveolus of yours, you were a coal miner, not farmer, and as a coal miner, you inhaled day after day little particles of coal, and you have lung fibrosis. So this lung here has created this thickness here because it's so used to getting bombarded by these coal particles that it's created a fibrous capsule so that it can protect itself. So now the thickness of that membrane is larger, and if it's thicker, it's going to be harder for you to cross it and bring that oxygen over. And the same way picking up CO2 is going to be the same. It's going to be harder. So membrane thickness is going to matter. What else is going to matter? And the fourth one here that's going to matter is the distance that oxygen or carbon dioxide, that gas needs to travel. So this region in yellow, I colored it up in yellow, is the region it has to travel. It actually has to cross the alveolus, come into this interstitial area, and then come into the capillary bed. Well, what if you have some sort of pulmonary edema and you have lots of fluid in this area? Then you have this big barrier, and this distance that it has to travel could be increased, and it also could be way more difficult because now you have more fluid in this area that shouldn't be there. So distance matters. So how do we measure gas concentration? And I've been telling you we don't really talk about it in milligrams like we would solute, but in terms of partial pressure. So it's the partial pressure that this gas expresses. So this pressure expresses gas concentration in a solution. It's going to have a certain amount of pressure in a solution of other gases. So we're going to have to compare that with the partial pressure in the air or in a fluid, for example, in the alveoli or in the blood. But if you haven't understood yet, hang on, because you will. So in this example, the partial pressure of CO2 in the blood, so if the partial pressure of CO2 in the blood is high, partial meaning there's all this pressure inside this vessel, this pressure of oxygen added on to the pressure of carbon dioxide. So you have to add those up together. But if we're just thinking of one, we're thinking of a partial, not the complete. So the partial pressure of CO2 in the blood is high here, and it's going to move over towards the alveolus. This slide is asking why partial. So pressure is exerted by a single gas, and the primary factor affecting that gas exchange is going to be measured in millimeters of mercury, and it's just think of it as partial as being a portion of the total of the gas where it's found. And atmospheric pressure is the combined pressure of all atmospheric gases. Okay, but when we're talking about pressure of oxygen, it's just a piece of that atmospheric, or of CO2. It's just a piece, it's partial. Atmospheric pressure at sea level is 760 millimeters of mercury. And in a pie chart, this is a real nice way of looking at it. If you took all of the gas that we inhale, atmospheric gas, most of it is nitrogen. 79% is nitrogen. About 21% is oxygen, and that's the one we are very interested in talking about a lot because that's what we're trying to get into our cells. And then we're also interested in carbon dioxide, which is a tiny amount. It's about 1%, we're going to say, a little bit less. And then there's argon and all of those are tiny amounts here. Okay, but we're more interested in the oxygen and carbon dioxide in a physio course. But let's continue to think about partial pressures. So nitrogen gas, if I'm telling you that it's 79% of the air that you inhale, then that partial pressure of nitrogen is going to be equal to 79% of the total atmospheric pressure, correct? Which is 760 millimeters of mercury. So we need to take 79% of 760, or multiply 760 by 0.79, and what we will end up with is 600 millimeters of mercury. So that is the partial pressure of nitrogen gas in the atmosphere at sea level. Now oxygen, when you're thinking of oxygen gas makes up 21% of the air. So we're going to take 0.21, multiply that by the 760, and come up with 160 millimeters of mercury is that partial pressure of oxygen that we have available at sea level when you inhale. 160, you have to remember that number. Remember that number. And of carbon dioxide around 1 or just below 1, so we're going to use 1 here, and we're going to call it 7.6 millimeters of mercury. That's the pressure that it exerts. Okay. Now, what if you're not at sea level? What if you are at the summit of Mount Everest? How is that going to be? And you know how hard it is to breathe because you must have read something or watched a movie. The altitude there is around, let's make it 29,000 feet. And the atmospheric pressure at 29,000 feet is way lower. It's about 253 millimeters of mercury. So much lower. So then, what's the pressure of oxygen? So if we're multiplying, I gave it away here, but if we're multiplying the partial pressure of oxygen, which we said was 21%, correct? So we're going back to the 21. 21% times 253 this time, because that's what that atmospheric pressure is. Then the oxygen pressure at that level, if you do your math, is only 53 millimeters of mercury. Very much lower. And you'll see after we continue this lecture or the next mini lecture on how crucial that is. That is barely enough to have enough sufficient pressure to cross the alveolus and get into the capillary. If you look at other cities, altitude of Mexico City, it's about 7,000 feet. So the atmospheric pressure is 589 millimeters of mercury. So what's the partial pressure of oxygen again? So you'd have to do your math and multiply your 21% times the 589 and come up with your answer. In Denver, atmospheric pressure of 628 millimeters of mercury. Again, 21 times that atmospheric pressure. And I'm giving away the answers here. In Mexico City, it's 123. And in Denver, it's 132 millimeters of mercury. So if you've traveled to these cities and you see how out of breath you are in the beginning because you're just not used to having that lower quantity of oxygen, or pressure of oxygen in the air, and it's more difficult to get that oxygen until you make more red blood cells. You're there for 3 or 4 days, you make more red blood cells, you've got more hemoglobin, and then you feel better again and you don't feel quite so dizzy. So we're going to stop this lecture here at the previous slide on partial pressures in these different cities and continue on with part 2 in the next series of slides. Thanks for listening. Bye, guys.